Figure 6 shows a sketch of the curve C with parametric equations as shown. Note there's a restricted domain for t, and that means the curve only exists between like these values, okay? It doesn't go on forever. That's going to be relevant later on. And the line L is the normal to C at the point P where t is pi over 4. Using parametric differentiation, show that an equation for L is given by this. Okay, so we're going to need to find dy by dx here, which using the chain rule is dy by dt, dt by dx, which you can then write as 1 over dx by dt, and you can just divide them. So dx by dt is going to be 2 sec squared t. Actually, the derivative is in the formula book. It's worth knowing though. And then slightly trickier one is dy by dt. So we're going to use the chain rule here. We times by the 2, because it's something to the power of 2. It becomes 4 sec t. And then we times by the derivative of sec t, which is actually sec t tan t. That's also in the formula book. But ultimately, it's then going to become sec squared t tan t. This is the great thing about sec. It kind of, when you differentiate it, the power actually stays the same. Okay, and that means that we've got 4 sec squared t tan t over 2 sec squared t. These cancel out, and then we have it 2 tan t. So when t is equal to pi over 4, we can work out what x is. That's going to be important. In fact, tan of pi over 4 is just 1, so x is just 3. Y is then 2 sec squared t. It's a little bit trickier. You could do it without a calculator. I'll just put it in, I think. So 2 divided by cos pi over 4 squared. That's my 2 sec squared plus 3. We get 7. And don't forget, we also need dy by dx to get the equation for normal. So I'm going to put pi over 4 into that. That's just going to be 2. So this is the gradient of the tangent. And therefore, the gradient of the normal will be the negative reciprocal, because they are perpendicular lines, minus the half. Okay, we're nearly there now. So that means y minus y1 is equal to m x minus x1, or you can use y equals mx plus c if you prefer. Y minus 7 is going to equal minus a half x minus 3. We're being asked to write it like this. I'm going to multiply it out. Y is going to be minus a half x plus 3 over 2 plus 7, which is actually 14 over 2. And there we have it. Y is equal to minus a half x plus 17 over 2. Next up, we're asked to show that all points on C satisfy this equation, i.e. we can transform the parametric equations into this Cartesian equation, albeit there is going to be a restricted domain. We're not actually asked about that here though. So let's start with the right-hand side. I'm going to do it bit by bit. So x minus 1, I'm going to square it as well. X minus 1 squared is going to become 2 tan t plus 1 minus 1 squared. These cancel out. I'm going to get 4 tan squared t. So then if I have a half, I think I can put it all together from here, half x minus 1 squared plus 5, then I'm going to get 2 tan squared t, because I'm just halving this, plus 5. And it doesn't at the moment look like 2 sec squared t plus 3, but that's because I need to use a trig identity. Sine squared plus cos squared is 1. Divide through by cos squared gives me tan squared, plus 1 is sec squared, and therefore tan squared is going to be sec squared minus 1. So 2 sec squared t minus 1 plus 5. That gives me 2 sec squared t minus 2 plus 5, which is 3, and that's equal to y. So definitely start with that one rather than with y and trying to get back. That's all we need to do as required. By the way, a harder question, and I just want to talk about it, would be to actually just be given these parametric equations and asked to find a Cartesian equation. And for this, I kind of want to do this part B in a different way then. So I would minus the 1 from x to make it 2 tan t, because I've got to think, how am I going to relate the tan t and the sec squared? That's the main idea. And then I'd do y minus 3 is 2 sec squared t. And then we think about how we can relate tan and sec. Well, we could square. We've got tan squared is sec squared minus 1. So I could do x minus 1. I guess I could put it over 2, but I think I'll leave it like this for the moment. X minus 1 squared is 4 tan squared t. So then I could make that sec squared minus 1, so it would be 4 sec squared t minus 4. And that will become 2 times y minus 3 minus 4, because it's 2 times 2 sec squared t, and I managed to link them together. Okay, it's just then perhaps making y the subject, which is what we're asked to do here. So I get 2y minus 6 minus 4, so 2y minus 10. Therefore, 2y is x minus 1 squared plus 10. So it is achievable, just you have to kind of this is such an important starting point if you're having to find a Cartesian equation and you're not kind of told it to begin with. There we go. Finally, part C. We're told that the straight line with this equation, y equals minus a half x plus c, where k is a constant, intersects c at 2 distinct points. Find the range of possible values for k. Now, kindly, we've been given the graph here. So actually, the gradient is the same as the gradient of that normal we found in part A. That's going to help us out a little bit. Remember, whilst we have this Cartesian equation, it's not valid over all x. It's only valid between these two endpoints, which we haven't actually worked out yet. But as I increase k, you can see actually I've only got 1 point of intersection here, so none of these are actually going to be valid. It's only going to be when I get to here that I suddenly get 2 points of intersection, and then decrease further until I get to here. So I'm going to deal with the bottom one to start with. This is actually going to be true in general. Even if I included all of the curve, there's going to be a value of k that's a cutoff for where I get 2 points of intersection. And it's going to be when I set the half x minus 1 squared plus 5 equal to minus a half x plus k. I'm going to be using a discriminant here to work out the different values of k. So I can times through by 2. I think that's a good start. X minus 1 squared plus 10 is equal to minus x plus 2k. Multiply this out. X squared minus 2x plus 1 plus 10, so that's plus 11, is minus x plus 2k. Then x squared minus x plus 11 minus 2k is going to equal 0. This is my c. Then I require for 2 distinct points that b squared minus 4ac is greater than 0. 2 distinct solutions. then I'll get 1 minus 4 times 1 times 11 minus 2k is greater than 0. I'll just expand it, I think. 1 minus 44 plus 8k greater than 0. 8k greater than 43. K is greater than 43 over 8. Okay, that is going to be that red line there. So I must have that. But now I want to find this other cutoff point there. And that's actually got nothing to do with the discriminant. It's all about the equation. So if I put in t equals minus pi over 4, one of the endpoints, actually that will give me the minimum value of x, because for positive t, I'm only going to pi over 3, tan's going to be positive, whereas for negative, tan's going to be negative. So tan looks like this. So the more negative, up to a point anyway, minus pi over 2, the more negative x will be. So t is minus pi over 4. If you put that in, remember we're working in radians, then we get x equals minus 1 and y equals 7. So that is that point there, actually. In fact, that's the one we need to use. I did find the other one while I was at it. T is equal to pi over 3 gives x equal to 1 plus 2 root 3 and y equal to 11. So we've actually worked out the domain in terms of x of the Cartesian equation would be minus 1 to 1 plus 2 root 3. And, well, actually, I haven't found the range because you'd have to find a turning point. Anyway, we're not interested in that. But what I'm interested in then is that green line that passes through minus 1, 7. So the maximum k occurs when y equals minus a half x plus k passes through minus 1, 7. So 7 here will equal a half, because it's a minus a half times minus 1, plus k. So then k will equal 14 over 2 minus 1 over 2, 13 over 2. And therefore, we require that k is greater than 43 over 8 from before. That was the red line, remember? That's the minimum value to get these two distinct solutions. It can't equal it because it just touches at that one point. But for the green line, it would just touch at that point where the curve begins, and that's included. So k is going to be less than or equal to 13 over 2. Okay, not easy, of course, but I hope this makes sense. Lots to think about. I've seen, even if you think like that was hard, I've seen lots of questions like this on Edexcel where you modulus functions and things like that, where you have to kind of be able to use the graph and work out this sort of thing. So don't give up on it. Keep practicing. Well done.